had a request to put off any graded homework to be due until next Wednesday. To tell you the truth, I wasn't sure what I was planning on doing quite yet. But if there is graded homework, it will be due next Wednesday instead of Monday. Okay. Next Wednesday is advising day. It'll be your last advising day for most of you, I think. We'll plan for interim and spring semesters, which does include topics in mathematics, which will be complex analysis, which is what Lauren is really excited about.
Yeah.
Actually, we do proofs in there, but there are less proofs in real analysis. There are fewer of them. They are not so many epsilon delta things, though there will be a little bit of that. It's actually more of a mixture of, it's sort of like halfway between multivariable calculus and real analysis. There's more proofs than multivariable calculus, but less than real analysis. We'll use Mathematica more, it'll be more visual than real analysis even. And so it's a pretty neat course. In fact, we're going to focus on worshiping God with our minds by the beauty that we see in complex analysis, because it is just such a beautiful subject. I didn't specialize in it in grad school, but it is, I think it's the most beautiful subject in all of math. It's just amazing. All right, what's the goal today? Well, I want to do one more application of the mean value theorem. I want to talk about that equivalent condition for Riemann integrability that involves the oscillation of the function. The facts to know from section 5.2, and then we're going to start section 5.3 a little bit, the fundamental theorem of calculus, focused on examples, not so much proofs today. All right, so what's the one more application of the mean value theorem I want to show you? Actually, most directly, it'll be an application of Rolle's theorem, but Rolle's theorem, remember, is a special case of the mean value theorem, when f of a equals f of b, right? You end up where you started, which was funny because you can also use the mean value theorem you can also use Rolle's theorem to prove the mean value theorem, a special case to prove the general case. It's a little strange that way. You can use the intermediate value theorem to prove the existence of roots. For example, take say a cubic like that, and say I want to prove that has at least one real root. Well, if the root was a nice number, you could maybe find that nice number and verify that's a real root, but in all likelihood it's going to be an irrational number. If you graph it, well, it's going to look about like this. And to a calculus student, it would typically be enough to say, hey, it just crosses the x-axis once. But we want to prove it crosses the x-axis once. We want to prove not only the existence of a root, but that it's the unique real root. How about existence? Use the intermediate value theorem. This is certainly a nice continuous and differentiable function everywhere. F of 0 is 2. F of negative 1 is negative 1 minus 5 plus 2 is negative 4. That is negative. You've got opposite signs for the function at 0 and negative 1. Therefore, by the intermediate value theorem applied to this function on the interval from negative 1 to 0, there's at least one real root. Okay, just like that is okay if I don't write that down. I'll say it again in case it went by too fast. To be official in applying the intermediate value theorem, you'd focus on the interval from negative 1 to 0. You'd say this is a polynomial. It's definitely continuous and differentiable on this interval. It's got opposite signs on the endpoints. Therefore, by the intermediate value theorem, there's some c between negative 1 and 0, where f of c equals 0. There's at least one real root. How would you show it's the only real root? You could use Rolle's theorem, the mean value theorem. And maybe the best way to do it is to argue by contradiction. Assume to the contrary. That there are at least two real roots. I want to show there's only one. will be two other complex roots. There we go, complex analysis again. But no other real roots. Assume to the contrary that there's at least two. Let's say C1 and C2 be two of them. Without loss of generality, C1 is less than C2. They're both roots, so f of C1 equals 0, and so does f of C2. The function values are the same. Therefore, by Rolle's theorem, f prime must have a root in between them. F prime must be 0 somewhere in between them. There must be a horizontal tangent somewhere. This function, again, is nice and differentiable and continuous everywhere. Rolle's, or you could say the mean value theorem. There exists a C between C1 and C2 in this interval such that f prime of C equals 0. But what is the derivative of this function? It would be 3x squared plus 5, so this would mean 3c squared plus 5 is 0. But that's impossible if c is a real number. There's your contradiction. Right? You know that's impossible if c is a real number. That has to be, this is a quantity bigger than or equal to 5 for all real c. So it's a contradiction, and therefore there can't be at least two real roots. There's got to be exactly one. We know there's at least one, but there can't be more than one. There's a unique real root when you combine these two theorems.
Can you walk through that one more time quickly?
Again, the intermediate value theorem proves there's at least one real root, and it's between -1 and 0. We want to show that's the unique real root, but there's no more than one. So assume to the contrary that there are more than one, there's at least two distinct ones. So consider two distinct real roots. Say C1 is less than C2. Because they're both roots, this is true. The function outputs are the same at the endpoints here of this interval from C1 to C2. The function's continuous and differentiable everywhere, in particular on this interval from C1 to C2. Rolle's theorem would say there's some number between them where f prime is 0, where the tangent is horizontal. What is f prime? It's 3x squared plus 5, so plug c into there. So for some real c, this is true, but that's a contradiction. That's impossible. Therefore, your original assumption must be wrong, and there can't be at least two. There must be no more than one, but there is one. So there's exactly one real root. All right, back to integrals. Let's go over, first of all, the facts to know from section 5.2. You needed to know these for the exam. You should know them for the future, too, for exam 3, because exam 3 will still be about integrals to some extent. The first fact in section 5.2 is stated, if f is Riemann integrable on a closed interval from a to b, then f must be bounded on that interval. Therefore, unbounded functions are not Riemann integrable. If you've got a rotor glass, I'm told you it's not Riemann integrable. Unbounded functions are not Riemann integrable on given closed and bounded intervals. Note, like I mentioned the other day, and this is important to realize, the existence of improper integrals of certain unbounded functions does not contradict this fact. The example I mentioned was the integral from 0 to 1 of 1 over square root of x. That's an unbounded function on the interval, but we often do this integral in calculus. And it's an improper integral because you've got the vertical asymptote at x equals 0 for this function. So technically speaking, it's a limit of proper integrals. I won't finish the calculation because I did it the other day. And this limit does exist. The area under this curve from 0 to 1 can be considered to be a finite area even though it has infinite extent upwards. That doesn't contradict the book's theorem, because that's a different kind of thing. That's a limit of proper integrals. It's a limit of Riemann integrals. We call it improper. It's not a proper integral in the sense that we're talking about in chapter 5. It's a different thing. Okay? It still makes sense to call it an integral, and we still do call it an integral, although we attach the word improper. And it still has applications, for example, to probability. I don't remember what the limit was. I think it was maybe 2. If the limit was 2, then this function would actually be a probability density function on the interval from 0 to 1. Because then the integral of that one would be 1. Was it 2? Do it in my head. Yeah, it was 2. The limit of this was 2. So if I divide this function by 2, I actually get a probability density function on this interval. It is a valid PDF. But again, this does not contradict the book's theorem. Okay? So for us in chapter 5, functions that are unbounded are not Riemann integrable. There are bounded functions that are not Riemann integrable, by the way. The simplest example of which is our favorite initial strange function. F of x is 1 if x is rational, and 0 if x is irrational. This function that's discontinuous everywhere, that function is bounded. But it turns out to not be Riemann integrable on any interval. Easiest way to prove that is with actually a theorem in section 5.3 that I haven't talked about yet. It's the first theorem in section 5.3, page 177 if you want to look there. Might as well go ahead and write down that theorem right now and explain why that proves, that theorem can be used to prove that this function is not Riemann integrable on any interval. This theorem, page 177, is that the page I said? Says, suppose f is Riemann integrable on a certain closed interval, from A to B, and, well, I forgot, is this an if and only if? No, okay. Okay, I'm going to state it a little differently. Suppose you've got a sequence of tag partitions. Strange, a sequence of tag partitions. Yeah, you can have sequences of anything. They don't have to be sequences of numbers. You could have, we're going to talk about sequences of functions in chapter 7. You can have sequences of tag partitions, one tag partition for each integer n. It could be a function from the natural number to the space of tag partitions. Weird. Okay, I'm not even going to finish writing that. Suppose you've got a sequence of tag partitions of the closed interval from A to B such that the corresponding sequence of norms of the tag partitions, that's a sequence of numbers, converges to 0, then the corresponding sequence of Riemann sums converges to the integral. So this seems kind of complicated, but actually the idea is pretty simple here. And it justifies, for example, if you know you've got a function that's Riemann integrable, if f is Riemann integrable on the closed interval, then you can calculate the integral as a limit of, for example, right-hand sums. A limit as n goes to infinity of, and let me go ahead and write the sum out with summation notation. A sum looking like this. Where delta x is b minus a over n, the length of the interval divided by the number of subintervals. Those are right-hand sums, like in calculus. Because using this for delta x, you're going to get the widths of all the subintervals being the same. And by letting n go to infinity, that delta x is going to 0 then. The norms of any of these tag partitions and the right-hand endpoints of the tags here is going to equal delta x. It's going to go to 0 as n goes to infinity. We have a sequence of tag partitions of the interval where the norm, in this case delta x, is going to 0 as n goes to infinity. The corresponding Riemann sum that you get there as n goes to infinity approaches the integral. This is the kind of thing we teach calculus classes. And this theorem justifies that we can do that. And it also can be used to prove this is not Riemann integrable on any interval, to consider the interval from 0 to 1. How could it be used to prove that that's not Riemann integrable? If you can find two sequences of tag partitions whose norms converges to 0, but the corresponding Riemann sums converge to different things, to different numbers, that would prove that it's not Riemann integrable. Because if it was Riemann integrable, both of them would have to converge to the integral. Catch that? Say that again. If you can find two sequences of tag partitions whose norms are converging to 0, but the corresponding sequence of Riemann sum values are converging to different things, two different things, that would mean the function can't be Riemann integrable, because if it were, they converge to the same thing. How do you do that? You could say t, what should I call it? P, maybe I'll put an R up there that's not a power. Rn, yikes, that looks like actuarial notation, doesn't it? Zach knows about that. Actuarial notation, superscripts and subscripts everywhere. Post-superscripts, pre-superscripts, okay. What is this tag partition for each integer n? What does R stand for? R stands for rational. We're going to have rational tags. Maybe it'd be better to put the R over here. Rational tag. If you have your tag partition have rational tags, of this form, ti, comma, xi minus 1, comma, xi, I'm going to be a little bit imprecise here. The distance here, delta x equals xi minus 1, is going to be constant for each I. So the norm of this tag partition is going to be delta x, and that's going to be a constant. These endpoints are going to be equally spaced. I'm saying that without writing it. If these t's, if I choose them to be all rationals, the corresponding Riemann sum is going to be 0 no matter what n is. Because, oops, sorry, it's going to be 1 no matter what n is. Because the output of the function for rational inputs is 1, and the interval has length 1. I should say here ti is rational. Did you catch that? I'm choosing, for any given n, a set of tag partitions, a tag partition set that is a collection of these intervals and the tags in such a way that the ti's in each of these intervals is rational. That means if I plug those t's into the function, I get 1. That means when I do my Riemann sum, this is 1 for all those ti's, and I'm really adding up the delta x's, which has to be the length of the interval, which is 1. Can you see where I'm going with this? With irrational tags, you're going to get 0. ITPN is going to be something similar, except the t's are going to be irrational. Okay, I'm not being real precise here, okay? Just trying to give you the idea. If the ti's for this particular sequence of tag partitions are chosen to be all irrational, which I can do, I can choose them to all be irrational, then in that case, the f of ti values are always going to be 0. I'm always going to get 0 for my Riemann sums. Zero for all n. So this would give you a sequence of Riemann sum values that's always 1. 1, 1, 1, 1, 1, it converges to 1. This would give you a sequence of Riemann sums that's always 0. 0, 0, 0, 0, 0, etc. It converges to 0, 2 different numbers. Therefore, the function can't be Riemann integrable. It is, however, Lebesgue integrable. This would be the easiest example of a function that's not Riemann integrable, but it is Lebesgue integrable. Not Lebesgue, Lebesgue. Everybody says Lebesgue. Okay.
Sounds better the other way though. Lebesgue.
Yeah.
Ouchie.
No, don't say that. And the integral of this function, the Lebesgue integral of this function, the same function here, over any interval here, is going to be 0. Intuitively, this is no proof. Intuitively, it's because the rationals are countable and the irrationals are uncountable. That's definitely no proof, because you can construct examples that go against that intuition. And actually, if I switch around the 0 and the 1, and I integrate over an interval from a to b, it becomes b minus a instead of 0. Intuitively, again, because the rationals are countable and the irrationals are uncountable. Again, that's no proof. Just a little bit of possible intuition that can mislead you if you're not careful. So, Riemann's integral is not as good as Lebesgue's integral. The theory of Riemann integration is easier than the theory of Lebesgue integration to understand, but it doesn't apply to as many situations, which is actually important. There are some sort of esoteric kinds of topics in probability, actually, where you need the Lebesgue integral to do what you want to do. So graduate school level probability requires the Lebesgue integral. What is that equivalent condition of Riemann integrability? it involves the oscillation of a function. Suppose, first of all, as a background assumption, f is bounded on a certain closed interval. Then f is Riemann integrable on that closed interval if and only if, for all epsilon greater than 0, there exists a partition, not a tag partition, but a partition P, just a breaking up of the interval. x0 is A, then x1 comes next, then x2, then x3, etc. xn is B. We're not talking about tags, no tag partitions here. If there exists such a partition where the sum I goes from 1 to n of the oscillations of the function over each subinterval times the corresponding delta xi, which is xi minus 1, is less than epsilon. That's an equivalent condition for Riemann integrability. And it looks like in this particular Mathematica notebook I got rid of that thing where I showed you the visual for it. Let's see if I can find another one. Here we go, it's right here. In the picture here, for the given partition, the things that you're adding up are really the areas of those orange rectangles. The oscillation of a function over an interval, remember, is the sup of the function on that interval minus the inf. Essentially max minus min for continuous functions by the extreme value theorem. So for example, on this interval, the sup of the function is up here, the inf is 0. Omega of f is the height of that rectangle. And delta xi is the width. The next interval, that distance is omega, the oscillation. Sup is up there, that value, inf is down there. The height is the omega, delta xi is the width. You're adding up the areas of those rectangles. If you can make the sum of the areas of those rectangles as small as you please, less than any given epsilon, by taking a sufficiently fine partition, like that, if you can make the sum of those areas as small as you like, then the function is going to be Riemann integrable. So you can see here as delta x goes to 0, it makes sense intuitively that the sum of those rectangles is approaching 0. The orange ones. I can choose different functions here. Doesn't matter. The sum of the areas of those rectangles is going to 0. Now we're not assuming continuity of f here. F doesn't have to be continuous. And so when you calculate the oscillation, the function may not attain a max and an min, but it is a bounded function, so there will be a sup and an inf. They might not be attained. But effectively, it's still could be thought of as the heights of rectangles and widths.
So that gives you, if it's Riemann integrable, if you can do that, but does it actually give you what the interval is?
Nope.
Okay.
It doesn't tell you what the value of the integral is, it just says this function's a Riemann integral. Yeah. That's a good point. Let's use this now to sketch the proof that a continuous function is Riemann integrable on a closed interval. Got a function defined in the closed interval and it's assumed to be continuous on the closed interval, then it's Riemann integrable on that closed interval. Let's sketch the proof. And this is the most obvious situation, as far as I remember in the book, where the Uniform Continuity Theorem is necessary. It's continuous on the closed interval. Therefore, by the Uniform Continuity Theorem, it's uniformly continuous on the closed interval, and that turns out to be necessary to finish the proof. Seems like a small use of Uniform Continuity Theorem, but it is actually very significant use. By the Uniform Continuity Theorem, the fact that f is continuous on the closed interval means it's actually also uniformly continuous on the closed interval. So there exists a delta greater than 0 such that the distance between f of x and f of y is less than epsilon. Probably would been better to phrase this as we can choose delta. I am choosing delta. For all x and y in the interval satisfying the condition of the distance between x and y is less than delta. That's just the definition of uniform continuity, which I can use the definition now because I know f is uniformly continuous on the closed interval, and I am using it really instead of just saying so there exists, I can say I can choose such a delta. That would be a better way to phrase it. We need to use the theorem I erased already. Wow. The equivalent condition for uniform continuity, I need to be able to find a partition of the interval from A to B so that the sum of the products of the oscillations with the delta x's for that partition is less than epsilon. We need to, again, find such a type, just a partition. And what you do is you could say let n be chosen so that, call it delta x, is b minus a over n is less than delta. That definitely can be done. Essentially, it's Archimedean property. Delta is positive. I can find an n so that this is smaller than delta, and I'm going to call that thing delta x. It's going to be the delta x for my partition. And in fact, now you could say let P be a partition consisting of